Welcome back to ChemDoctor, and what we're going to do in this video is determine the pH of a solution which is a mixture of two different weak acids, and along with that we're going to calculate the concentration of all anions that are also in solution. And this would be the fourth video in the playlist on weak acid and weak base equilibrium. So what we're going to do is we're going to mix two solutions. One solution is 0.1 molar benzoic acid with a Ka of 6.5 times 10 to the minus fifth, and we're going to put that in a solution with 0.1 molar hydrocyanic acid whose Ka is 6.2 times 10 to the minus 10th. And then what we're going to do is we're going to calculate the pH and the concentration of the conjugate bases for each of the respective acids. Now, both of these are weak acids. We don't have the chemical formula of benzoic acid. Just for the heck of it, I'll give you the Lewis formula. It looks like this. All right, and it's an aromatic ring. And then we have a carboxylic acid functional group coming off of that. With and a carboxylic acid is just that. It's a weak acid. There's the proton right there. We don't need the formula because what we're going to do is abbreviate this as HA, and that's part of the reason that I'm doing this way, is so that the viewer can get comfortable with this kind of notation. Now, here's the rub. We've got two weak acids in the same beaker with equivalent molar solutions. How do we figure out the pH of this? And what you're going to want to do is you're going to want to look at the Kas, because one of the two equilibriums is going to dominate over the other one. So notice that the benzoic acid has a Ka that's 6.5 times 10 to the minus fifth, while the hydrocyanic equilibrium is 6.2 times 10 to the minus 10th. So if we were to take a ratio of the two equilibrium constants, so I would take the larger one, 6.5 times 10 to the minus fifth, and we'll divide it by 6.2 times 10 to the minus 10th. We get a value that's about 500,000. All right, and what that means is that the equilibrium on the left, the benzoic acid, dominates the equilibrium on the right by about 500,000 times. So what that allows us to do is calculate the pH off of the benzoic acid. But things get a little complicated because that means that the hydronium ion concentration in the hydrocyanic equilibrium is going to be determined by benzoic acid, but also that's going to influence the concentration of the conjugate base that's going to form in the hydrocyanic equilibrium because of Le Chatelier's principle. So that was a mouthful, and I think you'll see what I mean once we get started. So let's go ahead and deal with this in a series of steps. So the first thing we're going to do, since we know the benzoic equilibrium is dominating, is we'll go ahead and we'll find the pH of the solution based on the benzoic acid. So I'm going to write my weak acid equation first thing, and we'll write it as HA. We'll put the water in to acknowledge the fact that this is a proton transfer reaction with water. We're going to form H3O plus, and we'll identify the conjugate base, the benzoate ion here, as A minus, and again, we're setting up our ICE, or the box. So before any reaction happens, we're going to have 0.1 molar of the HA. We're going to have 0 of the H3O plus and 0 of this. Now, at equilibrium, so after the reaction happens, the HA is going to be 0.1 molar minus X, and this will be X and X like that. So setting up our expression, we'll have X squared, and I'm going to go ahead and we're going to neglect the X immediately. All right, and we're able to do that because The equilibrium constant here is small. In fact, both of them are small. However, I am neglecting the x, and as we go through this, we're going to double check always. So we will calculate a percent dissociation for this soon after calculating our x values, which is also the 5% rule, and we're going to make sure that we're okay with that it was all right for us to have neglected the x before going on and calculating the pH. So this whole thing is equal to 6.5 times 10 to the minus fifth. So the x value will be equal to the square root of 0.1 times 6.5 times 10 to the minus fifth. All right, and so my x is going to be equal to 0.00255 molar. All right, and that is equal to the H3O plus. Remember, this equilibrium dominates, so this is going to be the H3O plus value in both equilibriums, and A minus, where A minus is the benzoate ion, this thing. All right, and now we're going to go ahead and calculate the percent dissociation. And remember, the percent dissociation is the same thing as the 5% rule. So I get two pieces of information out of this. I know how dissociated the acid is, and I also know whether it was okay to have neglected our X. All in one fell swoop. All right, and this is something you want to be in the habit of doing. So this is going to be times 100. And what I get is 2.55%. Shoot. All right, so we're well within the 5% rule for neglecting the X, and also we have a percent dissociation that's about 2.5%. All right, so now I'm going to go ahead and get the pH. So the pH of this is going to be equal to minus the log concentration point 0.00255, and what I get for my pH is about 2.59, which is in the range that you would expect for a weak acid that has a Ka around this value. All right, so now let's deal with the other part of this, and that's going to be the hydrogen, the hydrocyanic equilibrium. So we'll go ahead and write the equilibrium expression for this. And remember that the situation here is that the benzoic acid equilibrium is dominating this. Now, let's look at our ICE table or the box. So we have a 0.1 molar solution of the HCN to start with. The H3O plus. All right, here's the deal with that. We calculated it here, and because the benzoic acid equilibrium is dominating, this is the concentration of H3O plus that we need at this point. And if you've been with me through this whole series of videos, then you're going to realize something else. This is a common ion. It's common ion to two different equilibriums, because we have it here and we have it here. And both of these reactions are occurring in the same reaction vessel, right? Both of these solutions are together in the same beaker. This equilibrium on the left is dominating, so it's producing the hydrogen ion concentration, which is significantly greater than the hydrogen ion concentration that's going to be produced by the HCN equilibrium itself, right? Because this equilibrium, the benzoic acid equilibrium, is 500,000 times greater than the HCN equilibrium. So this is a common ion problem, and the significance of that is that if you remember back to solubility equilibrium, this, because of Le Chatelier's principle, is going to reduce the shift to the right of this equilibrium. All right, so this equilibrium is going to shift to the right to a lesser extent than it would be if we had the absence of this H3O plus concentration. So coming back to the issue at hand, after the reaction, this is going to be 0.1 molar minus X. The reaction definitely shifts to the right, see, because there's 0 of Cn minus to begin with. And Le Chatelier's principle says we've got to fill this concentration. So this is going to be, the hydrogen ion will be 0.00255 plus X, and the Cn minus is going to be X. So setting up the relationship now, I'm going to go ahead and neglect my X immediately. We are going to double check this, just like we did in the other problem, to be certain that we're okay with doing that. And I'll explain more about that when we get to that point. So this is our expression, and the whole thing is equal to 6.2 times 10 to the minus 10th. Okay, and my X value, doing the algebra, is going to be equal to 2.43 times 10 to the minus 8th. And that is equal to the concentration of Cn minus. Okay, now we need to be certain that neglecting the X here was fine. And what we're going to do is take a ratio of this value against the concentration of the H3O plus that came in from the other equilibrium, and that value should be less than 5%. All right. The concern here is that if we're getting a concentration of Cn minus, which is at a higher percentage to this value, 0.00255, than our percentage that we had over here, then we have to go back and utilize the quadratic equation, or the assumption to neglect the X in the sums would be incorrect. So if you run that number, what you're going to find is that we're well within our decision to have neglected the X. So in other words, if we take the ratio, I'm going to let the viewer do this on their own. If you take the ratio of this number against this number times 100, you're going to get a very small percentage, which is well within 5%, and so the assumption to neglect the X's was fine. So this is the concentration of the Cn minus. All right, and with that, I'm going to go ahead and close the video.